Hi everyone, welcome back. Hopefully you guys had a good 10-minute break. We are now going to continue on with our discussion of integration. So what we just showed is that we can find areas under curves by using integrals, and that allows us to find a couple of other things which are super helpful. So it allows you to find averages. So this is a really complicated notation for just saying that if you know like the integral of a curve between two areas, you can find the average value of that curve by just taking the integral, because that's the area, and dividing by the length that you are going by. So here, this is just the length, and this is the integral. So this is the total area underneath the curve for that length. Let's give a quick example of that. So let's say we go with our favorite parabola, f of x is equal to x squared. And I want to find the average value between -1 and 1. Okay, so how do I do that? Well, let's draw out our parabola. So let's do this. That's not a great parabola, but it'll have to do. And we're interested in finding this area. Right, so what we can do is we can get y average is equal to 1 over 1 minus -1, because this here is 1 and this here is -1, times the integral from -1 to 1 of x squared dx. Here, this is an x-axis, and so that's why we're integrating over dx's. And this is equal to 1/2 times 1 over 3x cubed from -1 to 1. And so this is equal to 1/6 times 1 cubed minus -1 cubed, which is equal to 1/3. And now this is because, if you notice, what we're doing is we're taking 1/2 times 2/3. And what you'll notice is that this total area is equal to 2/3, which you can get by using the integral. And then what we're doing is we're dividing by 2 because we have a length scale of 2. And so you end up with 1/3 for the final area, or for the final average value. So average value. And this makes sense, right? Because you're integrating, and so it gets you the area, and then if you want an average, you just take the area divided by the length. So like if you're thinking about driving in the car, well, why did you get 1 over 1 minus 1 minus 1? Ah, yes. So let me repeat that step. So here, what we have is we have a is equal to -1 and b is equal to 1, right? Because let's see here, this is b is equal to 1 and a is equal to -1. And so when you plug it into the formula, you want the distance between -1 and 1. And to get the distance between -1 and 1, well, this here is a, and this here, this here is b, and this here is a. And so that's why you get the 1 over 1 minus 1 over 1 minus -1. Okay. So basically, you can take averages because you can compute areas. If you think about it, if you want to get your average speed, if you integrate over your speed over some amount of time, then that gets you the total distance you traveled, and you divide it back out by the total amount of time, and it gets you an average speed. Okay, so now that we've done that, there are a couple properties of definite integrals that are useful. So let's go through them. So the first one is this constant multiplication. So we've already used this a couple times, but the basic idea here is that if you have a constant inside of an integral, you can move that constant out in front of the integral in terms of multiplication. And intuitively, so you get something like the integral from 0 to 1 of 2 times x dx is equal to 2 times the integral from 0 to 1 of x dx. And you can draw this out. And what all you're doing here is you have some lying here. Let's say this is 1. And what you can do is, if you're just multiplying by 2, that's doubling the height of the triangle effectively. So there. Okay, what are some of the other properties? Well, one of the other properties is that if you have the sum of different integrands, so by integrand, I mean the stuff inside of the integral, with the same bounds. So what we're trying to do here, we are saying that if you have the integral from 0 to 1 of 1 plus x dx, well, this is equal to the integral from 0 to 1 of 1 dx plus the integral from 0 to 1 of x dx. So basically, the summation, you can separate it out or bring them together. That is an x, not an alpha. Okay? And the last thing is you can sum, if you have the same integrand with touching bounds, you can add them together. So if you have, this is easier to understand if I draw it out. So let me write out an equation first. So let's suppose we have the integral from 0 to 1 sine x dx plus the integral from 1 to 2 pi sine x dx. That is equal to the integral from 0 to 2 pi of sine x dx. Why is that? Because if you have some, let's see, actually let me draw out here. And let's say we have a sine curve. So that's going to look something like this. And let's say this here is 2 pi, this here is pi, this here is 1, this is 1. Sorry, it's not to scale. Basically what we're saying is that if you want the integral of the area underneath all of it, well, you just take the area under one part of it and add it to the area under all the rest of it. Okay, so there are two different ways you can sum together things. So if you have the same integrand, by which, I mean here, if you have the same integrand with touching bounds, you can just combine them together because you're just looking at total area. If you have different integrands with the same bound, then you can combine the integrands together just by adding things together because it's additive. Okay, so let's go ahead and give you guys a chance to try that out. So I want you guys to, does the sum of the same integrand, yes, so some addition and subtraction are equivalent for these purposes. So I want you guys to figure out what this answer is. And you guys have a couple different choices. And basically what you're going to have to do is you're going to have to use the rules we just described to combine together sums or like subtractions. So one of the things you might note is, well, this looks like they have the same bounds. These look like they have the same integrands. Maybe you can combine them. Let's see. I guess this is a slightly more involved problem, so let me give you a couple of the intermediate steps. So the first thing you might do is you might combine together this 0 to 2 of x squared plus 5 dx, right? And over here you might combine these two, and you'll note that this is slightly more complicated because you're subtracting bounds, right? And so you can, you know that 1 to 3 is the same as 1 to 2 plus 2 to 3. And so, oh, can I go back to the property slide? Yes, I can. Yep. So these are the properties. So if your bounds are the same, then if your integrands are the same, but you have touching bounds, then you can add them together or break them apart. If your integrands have this, you have different integrands but the same bounds, you can just add them together or subtract them apart. Okay, so I'm going to, in the interest of time, I'm going to start working through the problem. I think that just ended up being a little bit more involved than I was expecting, but you guys can follow along, hopefully follow along. Yep. So yeah. So basically, what we have here is, you know that I'll give you another hint, which is this thing here is equal to the sum from 1 to 2 plus the sum from 2 to 3. Of that integrand. Because you can break it apart, right? So if you're taking the integral from 1 to 3, well, that's equal to the integral from 1 to 2 plus the integral from 2 to 3. So now what happens when we subtract this out is you end up getting the integral from 2 to 3 of x squared plus 5 dx. And now, again, you have the same integrand, but different bounds. This is from 0 to 2, and you have from 2 to 3. So this is all just equal to the integral from 0 to 3 x squared plus... we are starting to get some answers. Okay, nice. So let me just finish it out for those of you who are still a little bit confused. So you combine these together, you get this integral. So that's equal to the 1/3 x cubed plus 5x from 0 to 3, which is equal to 9 plus 15, which is equal to 24. Yep. So basically, there are these rules for combining things together, and they're really relatively intuitive. You can just think about like taking areas of things and combining them together, and when you can add or subtract those out. And so that's basically the reason we have these rules. Okay, so now let's move on to area between curves. So now we had the subtraction rule. We had this summation rule. You can add things together. It turns out that if you want to find the area between two curves, well, then you can just subtract out the. You can just take the difference of the integral of the two different curves. Now this shouldn't be too surprising because basically what we're saying is that if you have some function, let's say f of x, and you have some other function, let's say. My frames are dropping. Unfortunately, I don't think there's anything I can do about that. I should be, yeah, I apologize for that. Unfortunately, there's not much I can do about it right now. But thank you for warning me, and I'll try to look into it after class. Okay, but if you're taking the integral from a to b and you want the area between these two curves, so you want this area, then all you have to do is you have to subtract. You take the integral from f of x minus g of x dx. And note that it doesn't actually matter in this case if the bottom one becomes negative. So if you have something like this, because that negative area still counts the difference between the two. So in this particular case, doesn't matter that g of x goes negative. Is anyone else getting the frame dropping issue? I should be on pretty good internet here, but it's always hard to say. Okay. Yeah, sorry. There's not much I can do about Zoom doing that. In the worst case, you can go back to the video afterwards, since I'm recording this locally. So it will be on YouTube and my media with hopefully no frame drops. So it looks like it's an even mix. So it might be your internet. Hard to say. But, well, online teaching is what it is, and there's only so much you can do. Okay, but yeah, so you can get the area between two curves over some interval, and also, when a and b are unknown, you can compute intersection points to find the area between the curves. So, for example, if you have two curves that intersect, let's say we have these curves, one of the things you can do is you can compute these two intersection points and get all the area between the curves by first setting them equal to each other. So let me give an example of that. I'm sorry, I need to be watching out for the time because the last topic is integration by parts, which is usually quite tricky for people. And I want to make sure we have enough time for that. But yeah, so let's suppose we want to find the area bounded by the graphs of f of x is equal to 2x minus 2 and x squared minus 2. So let's draw this out. One of the things we need to figure out is, well, I already know where these things go, but let's say 1, 2, 3, 4, 1, 2, minus 1, minus 2. Okay, so 2x minus 2. Well, that's just a line with slope 2 with the y-intercept at y equal to minus 2. So let's say, let me do that one in blue. So this is going to be here, and so on. Yep. And let's say we have x squared minus 2. Well, that's going to be a parabola that goes something like, it should cross at 2 minus 2. But so what we can do is we can compute when these two things cross. So I already know when they cross, but we have intersections. Does the higher curve have to be first? Yes, it does. What will happen if you have the other curve first is you just get a negative area. So that should be pretty obvious when that happens, because you will get a negative area out of it. So you have intersections when f of x is equal to g of x. So that implies that x squared minus 2 is equal to 2x minus 2. Well, you add 2 to both sides and subtract 2x from both sides. So x squared minus 2x is equal to 0. And you have x times x minus 2 is equal to 0. So x is equal to 0 and 2 at the intersections. Now the area is just equal to the integral from 0 to 2 of f of x minus g of x, because you'll note that f of x here is the higher curve. So f of x minus g of x dx, which is equal to the integral from 0 to 2. You do the subtraction of 2x minus x squared dx, which is equal to x squared minus 1/3 x cubed from 0 to 2, which is equal to 4 minus 8 over 3, which is equal to 4/3. So that is the area between those two curves in that interval. And the reason we can do that is because we computed the intersections first, and then we just found what area is in between them. So sometimes this is useful, because if you have two different things that are both growing, so let's say you have two different populations of viruses. Let's say you have one virus that was the wild type, and then you have some mutant virus that spreads more quickly, then you might want to measure how much more quickly, how many more infections the mutant virus gives you. Yes, yeah, so Samantha's question, so f of x is just higher in the interval we are looking at, so that's why we know to use it first. Yes, if you end up with two curves that, and an interval where the curves aren't strictly higher than the other, well then you can't really talk about, then you'd have to break it up into like several different regions to find the area between the curves. But yeah, so you need the f of x to be the higher one. Okay, let's try this out. So what I want you to do is I want you to find the area bounded by the graphs of x squared and g of x is equal to x. So step 1, find the intersection points. Let me reset the... Yeah, so this is just, this is pretty straightforward. So x squared is equal to x, so that implies that x squared minus x is equal to 0, which implies that x times x minus 1 is equal to 0, which implies that x is equal to 0 and 1. So let's see, why is it not updating? Wait, did something go wrong with my... Oh, no, okay, sorry, it was just late. Okay, yep, and let's see, step 2, decide which graph is on top. So in this particular case, we have two different graphs. One of them is x squared, and the other one is y is equal to x. And so you'll note that, oh yeah, I didn't reset it, but yes, so you'll note that, oh, actually, wait a moment, interesting. So we need to decide which graph is on top, but you'll note that in this region between 0 and 1, the g of x is equal to x graph is actually on top. And so B is actually the correct answer here. So x is greater than x squared for x in this interval between 0 and 1. Also, another thing you can do is you can check that f of 0.5 is equal to 0.25, which is less than g of 0.5, which is equal to 0.5. Oh. And the last thing to do is just to compute the integral, and let me reset this. And I'm just going to go ahead and do it since we're running a little bit short on time, and I want to make sure to get to everything. And we've had a lot of this integral practice. It's just the integral from 0 to 1 of x minus x squared, because x is on top, dx, which is equal to 1/2 x squared minus 1/3 x cubed, from 0 to 1, which is equal to 1/2 minus 1/3, which is equal to 1/6. And note, what would have happened if you had done the wrong one on top is you just would have ended up with a negative area. And so that's a pretty good sign that you did something wrong. Okay, so I'm going to go ahead and move on to we have another 3 rules that we need to teach, and we have 30 minutes, so we're going to have about 10 minutes per rule. But these are a little bit complicated. So remember, we used to have a chain rule in derivatives, right? So if you don't remember, the chain rule is just if you have some function that's a function of some other function, so if you have f is equal to f of u and u is equal to u of x, then if you take the derivative of f with respect to x, then you get the derivatives of df du times du dx. Let me give an example of this. So an example of this would be something like d dx of 2x plus 1 squared. So what we can do is we let f of u be equal to u squared and u of x be equal to 2x plus 1. Then we have df du, because you're taking the derivative with respect to u, that's equal to 2u, and du dx is equal to 2. So this thing here is going to be equal to 2u times 2. And we can plug the u of x back in, so that's equal to 2 times 2x plus 1 times 2, which is equal to 4 times 2x plus 1. And you can further simplify if you want. So like, remember how I said that every single derivative rule has a corresponding integration rule? Even if sometimes it's harder to apply. So u-substitution is the opposite of the chain rule. So in this particular case, what you can do is, if we have an example here, if we have the integral of, say, 4 times 2x plus 1 dx, we can let u be equal to 2x plus 1, and then du is going to be equal to 2 dx. So here we're using differentials. So you can think of, if you were in the 137 calculus, or sorry, the A37 calculus class, we might talk a little bit more about how this is not rigorous and doesn't make sense in the sort of limit-based calculus that we've learned. You'd have to use hyperreal calculus to understand this, but it's a lot easier if we think of du as a tiny bit of on the u-axis and dx as a tiny bit on the x-axis, and we're just going to go ahead and run with that. So we have du is equal to 2 dx, so dx is equal to 1/2 du. You plug these things in, you end up getting the integral of 4u times 1/2 du, which is equal to the integral of 2u du, which is equal to u squared plus c, because of course you have a constant. So that's equal to 2x plus 1 squared plus c. And note that this is actually the opposite, because this is equal to 4x squared plus 4x plus 1 plus c, which is also equal to, oh wait, did I mess something up here? Something went wrong here. I'm not actually sure what went wrong here. 4x squared plus 4x plus 1 plus c. So that's equal to 4x squared plus 4x plus c. Oh, yeah, well, that's fine, because we're reversing our thing, and so our original thing was also 2x plus 1 squared, so that was 4x squared plus 4x. So we don't need that, so that all works out. Okay, so u-substitution is the opposite of the chain rule, but note that for the chain rule, we knew what our f and u were. But for u-substitution, you have to guess what our u is, and that makes things a little bit more difficult. And so the substitution algorithm is going to be, you're going to have to guess an appropriate u. And what that u is, unfortunately, I can't give you a general rule for it. And then you compute du, dx, and x. You substitute in to get rid of all the x's. You integrate as a function of x, of u, and then you convert back to x's. So let me give another example of this. Let's suppose we had the function integral 2x e to the x squared dx. So the first step is we're going to guess an appropriate u. I'm going to go ahead and guess the correct thing since I know what it is. If you don't know what the right thing is, well, you just have to keep on guessing. So you let u be equal to x squared, and then step 2. We have du is equal to 2x dx. And now we can plug these things in. So in step 3, we have that the integral of 2x e to the x squared dx is in the integral of e to the u du. So note that I chose all my variables very nicely to make these things all work out. And this is equal to e to the u plus c, because that's just the using the integration table. And come on. And you can plug back in with the value for u, so that's e to the x squared plus c. And now, if you're not convinced, what you can always do in these sorts of problems is you can check. So you can check to see if this is right. And the way you do that is you take the derivative d dx of e to the x squared plus c. The c disappears because, of course, the c is just a constant. And this ends up with e to the x squared times the derivative of x squared, which is 2x, by the chain rule. Okay, so the opposite of the chain rule is the substitution rule. Unfortunately, the chain rule was completely deterministic. You just went forward step by step, and you ended up with the derivative. Integrals are harder than derivatives because you don't actually know what the appropriate u is, and so you just have to guess. And sometimes you guess wrong, and then you have to start over. And you'll see that this is true also for other techniques we're using, like integration by parts. You sometimes have to guess the form of the solution, and if you guess it wrong, then you have to start over. And sometimes you won't even know whether or not the substitution rule or integration by parts works. And so there is a lot of trial and error in solving these types of integrals. So let's give, let's see. I am going to actually skip my next example since I just gave one example because I'm running a little bit low on time. And I'm going to give substitution for definite integrals. So remember, we had both definite integrals and indefinite integrals. So now, what happens when you do this u-substitution with a definite integral? Well, what happens is you're changing variables. And so this is a change of variables, and then you have to be careful because the limits of integration also change. So the integral from a to b of 1 plus x squared 2x dx, well, that is equal to the integral from x equal to a to x. So this, I'm just going to rewrite this out. Oh, sorry. By giving the explicit limits of integration. So those are in x-axis limits, x squared 2x dx. So now we've done that, well, what we want to do is we want to let u be equal to 1 plus x squared, and then du is equal to 2x dx. But now what happens here is when you're taking this definite integral, if you're substituting all these other things, you end up with a u du. But because your du is now here, you need to change your limits of integration, and you have u here. So u is equal to 1 plus b squared over, and u is equal to 1 plus a squared as your new limits. Okay, so basically when you, normally we don't write that the limits are explicitly of x or of u, but when you're doing these sorts of substitutions, you do have to be careful about that, because when you change what you're integrating over, you also need to change your limits. Because your limits are along the same axis of what you're integrating over. So this is equal to 1/2 u squared from u equal to 1 plus a squared to u equal to 1 plus b squared. And with a definite integral, you don't actually necessarily always have to go back to converting back to x's, because you can just directly evaluate this in terms of u's. So this is equal to 1/2 1 plus b squared wait, do I have another squared in there? Yes, I do. So there's another squared in there, so I'm plugging in u minus 1/2 1 plus a squared squared. Okay, so the important thing here is need to change limits of integration. You are confused, but you don't know what to ask. So, remember, when we're taking integrals, what you're doing is you're saying you have some curve, and then you have some value, x is equal to a, x is equal to b, right? And this is the x-axis, and this is the y-axis, or whatever. So now what we're doing is we're doing a change of variables. So we're converting this to some other axis. Let's say this is some other axis. Let's say this is the u-axis. I'm going to do a linear change of variables. That's easier to draw. But when you do this change of variables, you can't use u is equal to a. That's wrong. So you need to find a new value for u here and a new value for u there. Yeah, I apologize for that. We are moving super fast, and that is the state of this class. I was lost in the u-substitution. So I guess there are a couple different things let me try to do. Yeah, like I said, the class does move super fast, and that's because there's a lot of material we have to cover, and that's not something that's up to me. So let's try again. Okay, so we have several different steps. So we have this let u be, we have the change of variables. So this is our change of variables. We're just defining a new variable, u, right? So we're defining a new variable u as 1 plus x squared, because that's our guess. We're guessing that if we change this variable to this new variable u, then it'll be easier to integrate. How you come up with this guess, no one knows. There are some general heuristics, but that is something you just need to practice, coming up with these guesses. Now, when you have this, you might, what you need to do is you also need to convert your du into a dx, right? And so one thing you can do is you can take the derivative of u with respect to x. So d dx of u is going to be equal to 2x, right? But now, if we think about each of these derivatives as a fraction, which is not really the right way to do it, but what you end up with is du is equal to 2x dx, which is what we had there, by breaking it up. And so now that we have that, what we can do is we can plug in this 2x dx into there, and this u into here, and you end up with this thing here. You end up with that thing there, but of course, when you do that change of variables, remember your limits were also in terms of x. And so since we're changing everything to u, you have to change the limits also to be in terms of u. So here we had, so in the top one you had u is equal to b, sorry, x is equal to b, right? And you know u is equal to 1 plus x squared. If you plug in x equal to b in there, you get u is equal to 1 plus b squared. So this is what happens whenever you change the variables, and once you've changed the variables, you can integrate it as normal. Hopefully this will make a little bit more sense as we move forward, but I do think we need to move forward a little bit. Instead of asking, why would you do the substitution? Because, so in this particular case, you don't need to do the substitution because you can actually integrate each of these parts separately. So you don't actually need it. But in other cases, you will need to do the substitution because there won't be a rule. So in this particular case, you don't need to do it. I use this as an example because it's easy. But often in the harder cases, you don't. There isn't an easy rule, and you do need to use these substitutions in order to do the integration. Let me go on to the next step, and instead of asking you guys to try it out, let me just walk through them a couple more times. So in this particular case, we have the integral from x over 1 plus x squared dx. So this is something super complicated, and I'm going to guess, because I have the benefit of hindsight, that u is equal to 1 plus x squared, which means du is equal to 2x dx. And so this is equal to, and so here we had, if x is equal to 2, then u is equal to 5. If x is equal to 0, then u is equal to 1. And so when you plug this in, you get an integral from u is equal to 1 to u equal to 5 of 1/2 times 1 over u squared du. And now that you've turned it into this form, it's a lot easier to do the integration because this u substitution allows you to do the integral nicely. So this is equal to 1/2 times minus 1 over u from u equal to 1 to u equal to 5, which is equal to 1/2 times minus 1/5 plus 1, which is equal to 1/2 times 4/5, which is equal to 2/5. Where did the x on top go? So the x on top, note that you have this du is equal to 2x dx. So that means that x dx is equal to 1/2 of du. And so that is this x dx, which turned into this 1/2 du. Okay, and so I was going to ask you guys to do this, but this is, you don't need to actually fill out this poll. Okay, and for this next one, I give you the hint, but I'm not actually going to ask you guys to do it since we are running out of time. So this integral from this is sine x cosine x, what just happened? Cosine x dx, which is equal to minus the, so if you do this, du is equal to minus sine x dx by using derivatives. So this is equal to minus the integral from 1 over u du. So that's equal to minus log of the natural log of u plus c, which is equal to minus ln of the cosine of x plus c. What kind of guesses can you make? You can make any guess that you want. So du you get by just taking the derivative. So let's actually, so if you have u is equal to cosine, actually I shouldn't write there because that's about to get covered up. So here we had u is equal to cosine of x. So du dx is equal to minus sine x. If you move the dx out front, you get a value for du. You can make any guess that you want. Unfortunately, there isn't a general rule I can give you for what kind of guess. A lot of it comes with this practice, like recognizing different things, and sometimes you'll guess wrong. And that's unfortunate. And the next technique will be very similar to this. You just need to practice and get a sense of what kinds of substitutions make sense. Okay, so I'm going to talk about partial fractions next. One of the things that I can do is, so you guys should probably ask about the u-substitution and integration by parts in your tutorials as well. So hopefully your TAs can do a little bit more of that. If you still have questions, feel free to ask on Piazza as well. I know you guys haven't been using it that much, but I do check it. And so hopefully that can give you a bit of a better sense of these things. Now, sometimes there are all these techniques that let you convert one integral to another. Sometimes that makes it easier, sometimes it makes it harder. Part of the task of learning calculus is learning what types of conversions make things easier and what types of conversions make things harder. One of the techniques that you can use to break up a complicated expression into several simpler ones is something called partial fractions decomposition. So let me give an example of this. So if you have, say, 1 over 1 minus x squared, this is equal to 1 over 1 minus x, 1 plus x. And this is equal to some partial fraction by breaking up the denominator. 1 plus x plus b over 1 minus x. What exactly it is you don't really know, but you can solve for a and b. So you need a times 1 minus x just by multiplying together the fractions, plus b times 1 plus x is equal to 1. And so you get a plus b plus x times minus a plus b is equal to 1. And you have to match up the different variables. So a plus b is equal to 1. And minus a plus b is equal to 0. You solve that system of equations, you get a is equal to 1/2 and b is equal to 1/2, which implies that 1 over 1 minus x squared is equal to 1/2 over 1 plus x plus 1/2 over 1 minus x. Now you might be asking, why is this important? And this is important because sometimes you want to take the integral of that. So if you want to take the integral of 1 over 1 minus x squared dx, well, you can rewrite this. So we don't have a rule for 1 minus x squared. But what we can do is we can rewrite it in terms of this partial fractions decomposition. So that's 1/2 times 1 over 1 minus x plus 1/2 times 1 over 1 plus x dx. And once we've done that, each of these we can use a u-substitution to figure out. This is 1/2 times the integral of 1 over 1 minus x dx plus 1/2 times the integral of 1 over 1 plus x dx. Well, what are our substitutions? So if we have the integral of 1 over 1 minus x dx, that's equal to minus the integral from 1 over x minus 1 dx. And if we let u be equal to x minus 1, then du is equal to dx. And so this is equal to minus the integral of 1 over u du, which is equal to minus natural log of the absolute value of u plus c, which is equal to minus natural log of x minus 1, the absolute value of that, plus c. And you can do the same thing for 1 over 1 plus x dx, which is equal to the integral of 1 over u du. Here we're going to let u be equal to x plus 1, or 1 plus x, it doesn't really matter. Du is equal to dx. And so this is equal to natural log of u plus c again, which is equal to natural log of x plus 1 plus c. And so given all that, we know that this is equal to, this is equal to 1/2 times natural log of x plus 1 minus natural log of x minus 1 plus c. And yes, so basically by using these expressions, you can simplify or make things harder. You can simplify things around, and that allows you to take these integrals. And you'll most often see these types of partial fractions decompositions when you're taking an integral of 1 over something. So when you see these sorts of... Yeah, this is hard, so don't worry if you're confused. Unfortunately, this is one of the harder parts of integration, is these sorts of u-substitutions, and then integration by parts, which we're going to cover in a moment, is going to be even harder in some ways. But, I mean, that's the material. So, I have a thing for you to try out. I'm not going to do it right now since we're running out of time, and I want to give you a couple more examples so that you can rewatch in the video later. But, basically, you can solve for these. So there's a multi-step procedure. So the first one is you factor, and then you you solve for the different fractions, and then you take the integral using the u-substitution trick for each of the 1 over u. Okay, but the last thing is going to be arguably the hardest concept in integral calculus. So this is actually in some ways even harder than u-substitution, because you also have to guess, and you have to guess and break it up into 2 different parts. So remember, we had a product rule, and we didn't give a product rule for integration because it turns out that doesn't work. But if you take the derivative of u of x, v of x, that turns out to be equal to u of x times v, the derivative of v of x, plus the derivative of u of x plus v of x. So u of x, v prime of x, plus u prime of x, v of x. So let's go ahead and give a simple example. And this example will be d over dx, x plus 1 e to the x, which is equal to x plus 1 e to the x plus e to the x. That's equal to x e to the x plus 2 e to the x. Okay, so that's the derivative rule. So now the other thing we can do is, given this, we can go backwards. But note that in order to go backwards, you need to already know what's u and what's v. And that's not something we necessarily know in advance. So integration by parts is the opposite of the product rule. And I'm going to go ahead and give you the derivation, which basically involves the product rule, but reversing it. So you do not need to know this derivation, though I find it easier. So like, I never remember integration by parts, and I always rederive it, because it's just a consequence of the product rule. The basic idea here is that you have your product rule, and if you rewrite this out, you can take the integral of both sides here, and you end up with this thing here. So the integral of u dv is equal to uv times the integral of v du. This formula is super important, and you should memorize it. So memorize integration by parts formula. And so now that we have this formula, I can give you an algorithm. It's unfortunately not a great algorithm. So the integration by parts algorithm is, you have this formula. So this is something you know. And then if you have some integral, you guess which part is u, and you guess which part is dv. How you make that guess, that's a matter of some amount of practice, and you will guess wrong. The next thing you do is you apply the formula and, and hope that you can solve the integral of v du. So if it doesn't work, you try again with a different guess for u and dv, and you repeat over and over again. And sometimes it will turn out that you can't use integration by parts. It just won't work. So you might give up and try not use the sort of guessing if your guesses don't work. And it might not be something that you can solve using integration by parts, and you'll need other more advanced techniques. Unfortunately, there's no way for you to know that in advance, and you just have to try it. And you have to try it quickly. So let me go ahead and give you a couple examples to finish out the class. And so let's start with something relatively easy. So let's say ln of x dx. Okay, so this seems like it shouldn't be too hard. And I'm going to go ahead and guess the correct thing. I will show you an example where I guess the wrong thing in a moment. So I'm going to guess that this is u, and that this is dv. Let me use a different color. Okay, so these are my guesses. There's no a priori reason why you would choose them, except that they happen to work. So then you have u is equal to ln of x, and you have dv is equal to dx. So the next thing you do is, if you have dv is equal to dx, you need to figure out what v is, right? So v is going to be the integral of dx, which is going to be equal to x. You don't have to worry about constants here, since the constants will all fall out at the end. So this is taking the indefinite integral. And you take the derivative here, du is equal to 1 over x dx. So that allows you to solve for each of these different u, v, du, and dv. And you do a substitution. And so once you've done that, since you already have the integral of u dv, this is equal to uv minus the integral of v du, which is equal to ln of x times v, which is x, minus the integral of v du. V here is x, du is times 1 over x dx. And this is going to be equal to x times the natural log of x minus the integral of 1 dx, which is equal to x natural log of x minus x plus some constant. Okay, so what we did here is we had some magical guess that allowed us to separate out it into two different parts and then apply this integration by parts formula. Let's try it again with a slightly more complicated one, and we'll see what happens when you guess wrong. And you will guess wrong pretty often, probably. So if you have the integral of x ln x dx, well, let's start with a simple guess. So I'm going to guess u is equal to 1 and dv is equal to x ln x dx. Okay? So then we can compute du, which is just equal to 0. So you might already be thinking something's weird because you don't have it in terms of dx. And then you also get v is equal to the integral of x ln x dx. But this is not helpful because this guess doesn't make it simpler. This guess makes it you have the exact same thing. And so this guess does not work. So let's try another guess. So let's say that we guess that u is equal to x ln of x, v is equal to x. That's not something you know yet. U is equal to x ln of x, and let's guess that dv is going to be equal to the remaining stuff. So that's going to be equal to dx. Okay, so when you take the integral of this, that v is equal to x, and du, by taking the derivative, is equal to 1 plus natural log of x dx. And then you're left with x ln of x dx is equal to x squared ln of x minus, well, what are we minusing? So we need v du. So that's v here is x. So x times du. Du is 1 plus natural log of x dx. And you're left with this thing. X times plus x ln of x dx. Note that this is actually just as complicated as what you started out with. So this also doesn't work. And when you're doing integration by parts, often what will happen is you'll guess something and it won't work, and then you have to start over. So let's try again. What's another guess? Another guess that you might make is that u is equal to ln of x and dv is equal to x dx. So now, one of the tricks that might help you a little bit with integration by parts is you do want to separate out the integral into one part that's easy to integrate and one part that's easy to differentiate. So, and you have to balance those two because you need to both take an integral of the dv and take a derivative of u. So here, the derivative of u is easy, so du is equal to 1 over x dx. V, well, that's also not too bad. V is just equal to 1/2 x squared. And this will actually turn out to work. Oh, come on, let's go back. So turn out to work. So this will be equal to, well, you plug in uv. So what's u here? U is natural log of x. V is 1/2 x squared, so that's x squared over 2 times natural log of x, minus this integral of 1/2 x squared times 1 over x dx, because that's the du. And when you take this entire thing, that's equal to the integral of 1/2 x dx, which is equal to 1/4 x squared plus c. So this entire thing is equal to x squared ln of x over 2 minus x squared over 4 plus c. So because we chose the right guess, you can actually apply this integration by parts formula, and you end up with a closed form solution. Now, it takes a lot of practice to know when your integration by parts actually is working and when it isn't. And unfortunately, that is something that there just isn't a general rule for. Sometimes it'll be obvious because you have different parts that seem to make sense together. So the last thing, let me just actually do this one as well, because there isn't that much time in class for you guys to do it. I was going to have you guys do this one, but so what we do here, let's guess u is equal to x squared. That's something that's easy to take the derivative of. So then du is equal to 2x dx. And then dv is what's left over. So if u was that, then dv is what's left over. That's e to the x dx. But that's easy to take the integral of. So v is equal to e to the x. So this is equal to x squared e to the x minus 2 times the integral of x e to the x dx. And it turns out that sometimes you have to do it multiple times. But this is simpler. So if you do this multiple times, you get let u be equal to x, v be equal to e to the x. So you do repeat the process. du is equal to dx. dv is equal to e to the x dx. And, go back. And what you're left with is this entire thing is equal to x squared e to the x minus 2 times the quantity x e to the x minus the integral e to the x dx, which is equal to x squared e to the x minus 2x e to the x plus 2e to the x. And that brings us to the end of class. I apologize for how confusing some of the material is. It is the sort of thing that you just need to practice a lot. How do you know if you need to do it more than once? Well, if you've done it once and you don't have a solution yet, well, maybe you have to do it again. And usually the trick is, when you're doing all these manipulations, you want things to end up simpler somehow than what you started out with. So the reason this seemed to work is because x e to the x is simpler than x squared e to the x. And so you're trying to simplify at each step. And if you do that, then you are hopefully on the right track. So one of the things that happened before is, with our bad guesses in the previous example, is we weren't actually simplifying. And so where is the tutorial held? The tutorial will be held at this same Zoom link at 3 o'clock. So one of your TAs will be dealing with that. Okay, so I think that brings us to the end of class. I am just going to make a quick announcement that in the tutorial, I also have a practice. It's not really a practice quiz. It's just I've asked your TAs to explain CrowdMark to you and give you an example of like filling out things on CrowdMark, because that's how we're going to do the quizzes. So that will be in the tutorials today. So you should get when you post these slides later, can you add in the answer of the example you skipped? Yes, I will post in all the answers to the examples that I skipped. Actually, I might post a slightly different. Let me revise it. I might post a slightly nicer version since some of the wording is a little bit complicated. But yeah, no, the tutorial today is, so the only thing for marks are the actual quizzes. So if you already know how to use CrowdMark, you don't really need to like do the CrowdMark practice. But I don't know that everyone here has used CrowdMark before, and so that's why I'm asking the TAs to go over that with you all. I also have another question. Are there marks associated for attending the tutorials? No, there generally aren't. The tutorials are for your benefit. So if you already know all this material, then you only need to go to the tutorials with the quizzes. Having said that, I'm sorry that we got a little bit rushed at the end. Integration by parts and u-substitution are some of the harder concepts in integral calculus, and so hopefully after some practice, you'll get some practice in tutorial this week, you'll get some practice in tutorial next week. Hopefully, with some additional practice, you'll be ready for that Biley quiz in 2 weeks' time. Okay, I am stopping my recording, and I will post the cleaned up lecture notes to the website probably in a couple hours. So take care, everyone, and I will see you on Friday.